Today, we're going to continue finding derivatives. We're in the middle of chapter 3. And we've talked about some base derivatives, the derivative of a power function, an exponential function, trigonometric functions, at least sine and cosine. And we've talked about the rules, the product rule, the quotient rule, and the chain rule for making combinations of these functions with multiplication, division, or composition. Today, we just want to expand our list of base derivatives. So that's what this ... is. Let's add some more base derivatives. All right. We're going to start with our other common trig function, the derivative of tangent. We're going to find the derivative of tangent by writing tangent as a quotient, sine over cosine. We know from trig identities that tangent is sine over cosine. So I'm just going to rewrite tangent as sine over cosine. Once I write tangent as a quotient, I can use the quotient rule to find the derivative. So the quotient rule has a top and a bottom. So we'll have the top is sine x. And the bottom will be cosine x. Then I will need the derivative of the top and the derivative of the bottom. So the derivative of the top, sine is one of our basic derivatives. So the derivative of sine is cosine. The bottom is cosine, and the derivative of cosine is negative sine. So the derivative of the bottom is negative sine x. Now I have the 4 parts that I need to plug things into the quotient rule. So now we're going to use the quotient rule. And the quotient rule says the derivative of a quotient is the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So we're just following the quotient rule. Now we're going to simplify things a little bit because I have a cosine times a cosine. That's a cosine squared. So I have cosine squared. Then I have a sine squared times a negative sine squared. So the negatives will make a positive, and sine times sine is sine squared. And now I can just use trig identities on the numerator. Cosine squared plus sine squared is equal to 1. So we could say that the derivative of tangent is 1 over cosine squared x, better known as secant squared x. And this we could put in our basic derivatives toolbox. We can now just use the fact that the derivative of tangent is secant squared. The derivative of tangent is secant squared. So that means now that we know that the derivative of tangent is secant squared, we can now have tangent appear in our chain rules and our product rules and our quotient rules. So let's start coming up with some functions involving tangent and product rule, quotient rule, and chain rule. All right, so for example, let's suppose that f of x is the tangent of 5x cubed. Here we're going to be using the chain rule. The first thing that happens to x is that it gets cubed and then multiplied by 5, and then we take the result and plug it into tangent. So our inside function, I've been using u, I guess. Our inside function, u is 5x cubed, and our outside function is the tangent. So y is tangent of u. So this derivative is the derivative of tangent of something. So the derivative of tangent of a thing is secant squared of that thing times the derivative of the thing. Oops, 5x cubed. The derivative of tangent of something is secant squared of that thing times the derivative of the thing. The derivative of 5x cubed is 15x squared. It would be weird to put the polynomial after the trig function. We don't want to get confused that the 15x squared is part of the secant. So we can clean this up by putting the polynomial part first. 15x squared times secant squared of 5x cubed. Let's change things up a bit. Practice with using similar elements. Let's change things up a bit and see what rules apply and how we go about thinking through what the function is telling us. So let's build g of x and say g of x is 5x cubed times tangent of x. So here, if we think about what happens to x gets cubed, then multiply by 5, and then we have to hold that and take the x and plug it separately into the tangent and multiply those two results. So this tells us that we're dealing with a product of 5x cubed and tangent of x. Because I got to hold those results and multiply them together instead of just taking the result of 5x cubed and putting it into the tangent. So I'm going to separate this into a first and a second. So the first will be the 5x cubed, and the second will be tangent x. Now I need the derivative of the first. The derivative of the first is 15x squared, and the derivative of the second, the derivative of tangent is secant squared x. Now I'm ready to put things together in the product rule. So g prime of x is the derivative of the first times the second plus the first times the derivative of the second and we can just leave this one at that. There is a 5x squared that we can factor out of this, but we don't really gain much out of doing that. If we had to go on with this function and do some more stuff with it, then maybe that would be useful. It might be useful to rewrite this at factor out the 5 and the x squared. But if we're just practicing using the derivative rules, it's not that important. That leaves a 3 tangent x and an x secant squared x. That's not really an improvement. So we just need to practice reading our functions and deciding what rule to use. Let's build another basic function. Let's suppose that we wanted to know the derivative of secant x. When we take the derivative of tangent, we end up with the derivative with a secant squared. So it makes sense. We might want to, if we take a second derivative, we're going to need to know the derivative of secant. So let's calculate the derivative of secant. I'm going to rewrite the secant as 1 over cosine. I'm going to do the same thing that we did with tangent. I'm going to write secant as 1 over cosine. I can also write secant as the whole cosine of x all to the -1, the reciprocal of cosine of x. And I'm going to write it this way so I don't confuse the reciprocal of cosine x with the inverse cosine. So we have a few options of what we can do here to find the derivative. If I look at secant as 1 over cosine, I could try the quotient rule to find the derivative. So maybe we read it as 1 over cosine, and we try the quotient rule. Or we could read the derivative of as cosine of x all to the -1. And then for this, we would read it as a chain rule. They should both work out to the same function, which means now I have to do both. My second choice would be to use the chain rule because the numerator for the quotient rule is constant. And so that the derivative at the top is going to be a 0. So I know I'm only going to end up with one term. My third choice would be to use the quotient rule. My first choice would just be to remember that the derivative of secant is secant tangent. But we don't know that yet. We're trying to figure that out. Let's go in reverse order. Let's use the quotient rule where the top is 1 and the bottom is cosine x. I need to take the derivative of the top, which is 0. And I need the derivative of the bottom, which is minus sine x. Now I can put things together with the quotient rule. So the derivative of 1 over cosine x. I'll have the derivative of the top times the bottom minus the top times the derivative of the bottom all over the square of the bottom. So that first term drops out. 0 times cosine x is 0. And the -1 times sine x is positive sine x. So I end up with sine x over cosine squared. This is not the normal way we report the derivative of secant. We split the sine over cosine as tangent, and then we write 1 over cosine as secant. So we tend to rewrite this as sine x over cosine x times 1 over cosine x, and just split the cosines in the denominator. Sine x over cosine x is tangent, and 1 over cosine x is secant. So the derivative of secant is secant tangent, or tangent secant. And this will count as a new basic derivative. The derivative of secant is secant tangent. I know when we were working out, I wrote tangent secant. That's because I split the sine off over cosine first. And so tangent showed up first there. But the way I say it on the regular is secant tangent. So the derivative of secant x is secant x tangent x. Now we can also find the secant, the derivative of secant, by thinking of the reciprocal of cosine. So let's look at this as a chain rule problem. So let's suppose that instead of thinking of the quotient rule, we thought of the derivative of secant x as the derivative of the reciprocal of cosine. So in this case, we're viewing it as the cosine x function being plugged into the 1 over x function, or the x to the -1 function. So our inside is cosine x, and cosine x is plugged into the -1 function. So the derivative of something to the -1 power is -1 u to the -2. So we'll have negative, oh, let's do this. Great. -1 times u to the -2 power. That's just the derivative of anything to the -1 power is -1 times that thing to the -2 power. And the thing in this case is cosine x. But then the chain rule says we have to multiply by the derivative of the inside, and the derivative of cosine is negative sine x. So we arrive at the same place we did when we thought of using the quotient rule. The negatives cancel out, and I have a sine x over a cosine squared x. which we can write as secant x, tangent x, the same way we did before. So here's one of our new core derivatives. The derivative of secant x is secant x tangent x. Now we can use secant with our product rule, quotient rule, and chain rule, just like we did before. So if, for example, I guess this was not so much of an example as a new core derivative. If, for example, I have a function of x, let's say capital F of x, is the secant of 5x to the third. We're going to read the inside as 5x to the third. And the outside function, or the function that the 5x to the third is plugged into, is the secant function. So my y function is just secant of u. So we're going to use the chain rule, because the first thing that happens to x is it gets cubed, then multiplied by 5, and then we plug into the secant function. We take the result of 5x cubed and plug it into the secant function. We're making a composition of those functions. So the derivative, f prime, capital F prime, is the derivative of the outside with respect to the inside. So the derivative of secant of u is secant u tangent u. And in this case, the u is 5x to the third. Secant is weird because the x shows up twice in its derivative. It's secant x tangent x. So when we're using the chain rule, it's secant u tangent u. And then I just have to multiply by the derivative of the inside, which is 15x squared. This would be a weird way to write this with the polynomial way down here at the end, so we'd probably write that first. 15x squared secant 5x cubed times tangent 5x cubed. Just because we wrote the 5x cubed twice because the form of the derivative of secant doesn't mean that we have to multiply by 15x squared twice. We write the secant of 5x cubed times tangent of 5x cubed. All this is dy du, and I just multiply by du dx. So we have dy du times du dx. I don't put du dx twice. That's not what the chain rule says to do. That's a really important thing to note. We don't just want to think of this as some kind of visual process where we just copy what's going on and say, oh, I'll have to do it twice. That wouldn't make sense. That would be a weird conclusion to come to because we want to use the chain rule where we're taking dy du and then we multiply by du dx. It doesn't say to multiply by du dx a bunch of times. It just says multiply dy du by du dx. A lot of times I describe the mechanics of calculus or algebra as pushing symbols around a page. But we do that for a reason. Any questions? Just like before, we got to make sure we read our functions correctly. So let's look at g of x. Let's make a new capital G of x. And I'm going to do pretty much the same thing I did last time. Capital G of x, I'm just going to move the 5x to the third as a factor before secant of x. Once again, the read on this problem is we look at what happens to the x. We take the x, we cube it and multiply by 5, and then we hold that result. Then we take the x and separately plug it into secant, and then we multiply the two results. So this is a product rule problem, where I have a first and a second, and a derivative of the first, and a derivative of the second. So the first is 5x to the third, and our second will be secant x. The derivative of the first is 15x squared, and the derivative of the second is secant x tangent x. Got all my 4 parts down. I'm ready to plug into the product rule. So g prime of x will be the derivative of the first times the second plus the first times the derivative of the second. So here's our result using the product rule. We might notice that there's a 5, an x squared, and a secant in common. We might want to factor that out for some reason. So if I factor out a 5, an x squared, and a secant x, that will leave behind a 3 and an x times tangent x. Which is not obviously superior to what I had before. If I had to take another derivative, this would be the way to go, because now I just have to use the product rule one time. If I had to take the derivative of the previous line, I'd have to use the product rule on the first term and then some kind of expanded product rule on the second term, because there is a first, second, and a third in the second term. So I'd have to use an expanded product rule. But if I factor out the 5x squared, oh, I still have, there's an x squared, I forgot about that. I still have 3 factors. I'd have to use an expanded product rule with the first, second, and a third. And when I take the derivative of the third, I'm going to have to use the product rule again with an x tangent x. So I'm not sure which one of these would be better in general. Maybe you just like things factored. Any questions? One thing to notice about this G prime, I deliberately made this 5x cubed times secant, whereas the previous one we had 5x cubed times tangent. Notice that in 5x cubed times secant, the derivative had a 15x squared and a secant, then a 5x cubed and a secant x tangent x. In the original, or the one that we did on the previous page, I had 5x cubed times tangent, and the derivative was 15x squared times tangent plus 5x cubed times secant squared. So there was still that 15x squared and the 5x cubed. And then I had times the second and the derivative of the second. We should start noticing similarities in our problems. But one of the most important things we need to be able to do is to read what the function is telling us so that we can decide when to use the chain rule and when to use the product rule and when to use the quotient rule. Any questions? Comments? Snide remarks? All right, so today we got two new core derivatives. The derivative of tangent is secant squared. The derivative of secant is secant tangent. And we're going to say them with shorthand. That's a better way to remember it, so we don't have to say the of x all the time. But if we find ourselves in court and we're standing in front of Judge Judy, we should say the derivative of tangent x is secant squared x, so that we are more clear. When we say the derivative of secant is secant tangent, that's just us shortening it as a mnemonic to help us remember. I'm not sure if there's a common mnemonic for derivative of secant is secant tangent other than that. I'm not very good at mnemonics. My mnemonic for remembering my trig function ratios is that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. My trig teacher tried to teach us like, oh, heck, another hour of algebra. I'm like, oh, that means I have to remember that it goes in the order sine, cosine, and tangent. And then they also, another trig teacher tried to teach us SOHCAHTOA. And so, but all that meant I just had to remember multiple things when I could just remember sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Mnemonic devices might work for you. They've never been particularly effective on me. I don't know why. Although with greater than or less than, I definitely do the crocodile eats the bigger thing. So. Any questions? Comments? Deep thoughts? How's everybody? Okay. Everybody's blurry. Now we're less blurry. So continue practicing on your derivatives. One good place, great place to go would be in the chapter, at the end of the chapter, there's a chapter review where it's just in problems 1 through 1,000, do a bunch of derivatives, find the derivative of the function. So I'm not sure what page that's on. Let's see. Jump all the way to the end. But I think it should be included. Might not be. Might have taken that away from you. Oh, nope. At the end of chapter 3, there's a whole section called Review Exercises and Problems for chapter 3. And the first instruction is find derivatives for the functions in exercises 1 through 73. So if you're looking for problems to practice on, there's 73 of them right there. If you come across something that we haven't gone over in class, like the natural log, derivative of natural log, or the derivative of arcsine, or the derivative of arctangent, then you skip those and move on to ones that you do, because they're going to be all mixed up in the review section. But that would be a great place to practice. In a couple of weeks, if we start having some quizzes or tests and you start asking me, how can I practice this? Or how can I get better at this? I'm probably going to say, have you done those 73 problems at the end of chapter 3? If you say yes, expect to have to show me that you have done those problems. So don't just say yes when you haven't done them, because I might go, great, show me. Which ones were you stuck on? Any questions? All right. All right, that's going to do it for today. I will see you all on tomorrow. If you have questions, stick around. Everybody have a good day, and thanks for playing.